Welcome to another video on linear algebra. Today we'll be discussing about determinants. Determinants are one of the properties that matrices, more particularly square matrices, can have. And so let's just get right into it. So determinants, as I mentioned, are unique features in square matrices. Their notation is just basically you can just say determinant of A, where A is a matrix, or you could just put det in parentheses A, or kind of like absolute values of A. Another way you could do it is to explicitly write down the matrix and then put them in like absolute value bars, as I have here. To calculate them, well, that's kind of a different story. There is one way of calculating that works with every n by n matrix, although it has to be greater than 2. The easiest one to calculate is the determinant of a 2 by 2 matrix, because that is just simply AD minus BC. So we just basically multiply its diagonals and then, or multiply the main diagonal and then subtract it by the other, I guess, diagonal. And so yeah, that's how you calculate it for a 2 by 2 matrix. Another thing to note is that the determinant of any identity matrix, doesn't matter what size, is simply just 1. You can prove it rigorously. You're just gonna get 1. It's yeah, you're just gonna get 1 with any n by n square matrix. Its determinant would just be 1. Another way you could calculate it is through, I guess, special matrix. So one of them is a diagonal matrix. So the determinant of a diagonal matrix is just the product of the diagonal. Likewise, the determinant of a upper or lower triangular matrix is, again, the product across the main diagonal. So what you can do is just, if you know the matrix is it's just a diagonal matrix or has an upper or lower triangle, you can save yourself the time and just multiply the main diagonal, and that would just be your determinant. Another way you could calculate the determinant is through square reduction. And what that basically means is if we have an n by n matrix, we just take the determinant of like the smaller square matrices. For example, if we have a 3 by 3 matrix, we can just reduce them to a 2 by 2 matrix and then add them all up. But it's not simple as just finding any 2 by 2 matrix and then taking the determinant on a 3 by 3. There's just certain things you have to do, but we'll do them in the examples. Another way you could calculate them is through blocks, and there's only a specific case where you can do this, and that is again, I'll see if I could, or we'll do it in one of the examples. And so it's just, it can actually just make your life so much easier if it's like a 12 by 12 matrix using the blocks method, but it has to satisfy a specific and very strict condition, unfortunately, in order to do this. Another way you could do this is through expansion. I don't know what the proper term is really, but I call it expansion, but it's only for a 3 by 3 matrix. And what that basically means is you take the 3 by 3 matrix and then you add 2 more columns, and the 4th column would be the same as the 1st column, and the 5th column would be the same as the 2nd column, and then you just multiply diagonals and then subtract them. Again, I will do these in examples. Another neat thing about determinants is that you can manipulate them. So when you manipulate a matrix using row reduction, you can change its determinant. And what I mean by row reduction, row operation is, multiplying, what do you call it? Multiplying a row by a constant will just ultimately scale that determinant by that same constant. If we switch to rows in the matrix, we just multiply the matrix by -1. And then lastly, if we were to add one row to another, it does nothing. And so, and those are the three row operations. It's multiplying the row by some constant c that's not equal to 0, switching to rows, and then adding a row by a multiple of another. And this can become a bit tricky if you're not keeping up with what you've been doing. But if you want to save some time and not worry about what happened to the determinant, highly suggest adding a multiple of one row to another, as the determinant just remains the same. And then lastly, I believe, is we're going to discuss about properties of determinants. Yes, they have properties. They are some things that you have to keep in mind as they will be useful in the future. The first one is, I mentioned before, the determinant of an identity matrix is equal to 1. Another one is the determinant of a transpose is the determinant of the original matrix. And then remember, or if you recall, the transpose of a matrix is just switching the rows to columns. So rows become columns and columns become rows. Keep in mind, determinants are only valid in square matrices. So our matrix here have to be square matrices. Another thing is if a matrix or row, or if a matrix has a row or column, my bad, of zeros, then its determinant is 0. That ties in with inverse matrices, in which, well, more particularly the rows. So if you have a row of 0, then that means its rank is less than the number of columns. So that means you'll get a determinant of 0, which means it is not invertible, that matrix. But yeah, a matrix with a column or row of zeros has a determinant of 0. Another thing, if two rows or columns are scalar multiple of each other, then its determinant is also 0. The reason is because one's dependent on the other. What you can end up doing is you can do a row operation on one of those rows or columns, and you'll end up getting a column or row of zeros. As I mentioned on the previous bullet point, if a matrix has a row or a column of zeros, the determinant is 0. Wow. Another thing is, if an n by n matrix is multiplied by some scalar k, then its determinant is the determinant of the original matrix multiplied by k, or c, raised to the n, which n is the number of columns. So if you have a 3 by 3 matrix whose determinant is 2, and you multiplied it by 3, then our new determinant would be 2, which is the determinant of A, multiplied by 3 raised to the 3, or to the third power. So that would be 3 times 3, 27. 27 times 2, 54. Wow. Another thing is, for any two n by n matrix, A and B, its determinant, if you multiply matrix A and B together, is the same as the determinant of A multiplied by the determinant of B. That's really neat. That's actually really neat. It can be useful. Another thing is, I mentioned this on our lesson on inverses. A square matrix is invertible if and only if the determinant is not equal to 0. So if it's anything but 0, it is invertible. Lastly, would be the determinant of any inverse matrix is just the inverse of the regular determinant. So if we had a matrix that has a determinant of 3, its inverse would be a 1 over 3, which is pretty neat, you know. And yeah, that pretty much concludes this lesson on determinants. Again, we'll do a couple of examples, primarily focusing on finding determinants on different cases and knowing when to use special, or I guess neat tricks on when calculating determinants, i.e. whether it's diagonal, upper or lower, probably a block case, and then a couple of 3x3 matrices, since there's multiple ways to calculate a 3x3 matrix. That's pretty much it, and I'll see you guys in the blackboard.